Welcome to Energy Talks, a regular podcast series featuring expert discussions on power system testing, data management, cybersecurity, and important trends in the power industry. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. In Energy Talks episode 82, we spoke in detail with our experts Christian Raunick and Theodore Connor about the revision of the EN50522 standard for earthing testing. The focus was on how this European standard for earthing measurements was developed, the work of the Standards Committee, and the recent changes to the content of the standard. In this episode, we dive even deeper into the subject matter and discuss the impact on measurements using the revised EN50522 standard with Josef Schmidbauer, an expert in earthing, also known as grounding testing, and product manager of OMICRON's Campano 100. Josef highlights the implications of the EN50522 standard, related measurement procedures, safety considerations, and the recent changes made to enhance safety and reliability. Josef also discusses the importance of touch voltage measurements, interference suppression methods, and the advantages of the newly introduced frequency-selective method for earthing and grounding measurements. Lastly, he explains how modern testing equipment allows for safer and more efficient earthing and grounding testing. Josef has joined us as a guest before in Energy Talks episode 66 about power system testing in the age of carbonization, and episode 19 about earthing grounding testing to prevent electrical shocks. Josef, welcome back to Energy Talks to speak with me about the impact of the latest revisions of the EN50522 standard on earthing and grounding measurements.
Hi, Scott. It's a pleasure to be here.
Well, thank you again for being here with us. Josef, we talked in detail about EN50522 in episode 82 of Energy Talks. Could you please say a few words about what the EN50522 standard is all about?
Yeah, the EN50522 is a standard which is about designing and testing grounding system for high voltage systems. And it defines various things from the exact design of the grounding systems, the required materials, and so on. And it also includes the testing of these grounding systems.
Okay, so the EN50522 standard is essentially a European standard. Does it have implications in any other regions of the world?
Yeah, actually, there is no IEC standard for this. So there is the European standard and the IEEE 81 standard. And in some regions worldwide, they use the European standard, the 50522. In other regions, they use the IEEE standard. And this is also the reason why we have different words here. For example, the IEEE standard are using the US words, which is grounding. And the EN standard 5522 is using the IEC term, which is earthing. And here in this podcast and also here at OMICRON, we use both in the same way. So sometimes we say grounding, sometimes we say earthing. In our official documents, we usually say earthing because that was decided to be so. But nevertheless, if you hear earthing or grounding, we both mean the same.
Josef, thank you for that explanation. Could you please tell us more about these measurements and procedures that are described in the standard?
Yes, Scott. So the most used measurement in this standard is the so-called ground or earth impedance measurement. So again, in the EN standard, it's called earth impedance measurement. This involves the injection of a test current in a sufficient distance of the grounding system under test. And this sufficient distance is then called remote earth or distant earth. Then the voltage difference between the grounding system and a voltage probe in a sufficient distance is measured, and then it's called the ground potential rise, GPR, or the earth potential rise, EPR, in the European standard 50522. As soon as you have this potential difference to distant earth or to remote earth, you can calculate then the impedance of the grounding system using the injected test current. Depending on the potential fault currents, this impedance must then be below a certain value to ensure that the system is considered safe according to the standard. That means that the ground potential rise or the earth potential rise in the case of a fault will be below the permissive limits.
Okay, so you mentioned safe. What does safe mean in this context?
Safe means, for example, if a person is next to a fence of a substation or a power pole and touches the system, and if there is a fault in the system at the same time, or even during the normal operation, the voltage must be low enough to not harm the person, so that the person won't experience a dangerous voltage. These voltages are usually referred to as so-called touch voltages.
Okay, so why do we measure the grounding or earthing impedance and not the touch voltages?
That's a very good question. So you're right, the touch voltages are the much more important factor. So usually you would like to ensure that all the touch voltages are below the permissive limits. But of course, the standard specifying you have to measure it on relevant points. So you have the discussion what is relevant. There are a lot of different measurements. Therefore, the standard has an easier option to ensure that the grounding system is safe, and that's to measure the ground impedance or the earth impedance. If the ground or earth impedance is low enough, then the touch voltages are assumed also to be within a safe limit. This simplifies the testing very much because only a single measurement is needed instead of a lot of different measurements. However, after the measurement, if it turns out that this impedance is too high and you have a high value here, then you need to measure all the touch voltages to prove that they are below the permissive limit. For example, if you have a standalone high voltage pole or transmission tower, that's usually not necessary because a simple measurement of the earth potential rise or ground potential rise and the calculation of the earth or ground impedance is sufficient. However, if you have, for example, a larger substation, it can be beneficial to measure also the touch voltages. For example, substations often have fences with potential control measures like buried metallic conductors. These conductors are used to reduce the touch voltages by providing some potential grading. And of course, such buried metal conductors can erode over time. So the measured touch voltages can then be higher. And so it's useful to measure these voltages instead of just trusting the earth or ground potential rise.
How much time are we talking about in doing both measurements?
So if you do only the ground potential rise or the earth potential rise, you are faster, of course, because you don't need to measure all the different touch voltages. So for a regular transmission tower, I would not invest the time to measure also the touch voltages. But of course, if you have a big substation and you need anyhow to inject the test current in a remote distance, you need a lot of time to install this current probe in a sufficient distance and so on, then I would also measure the touch voltages. Because if you talk about the total time demand for the measurement, it's not a big difference. So maybe worth to mention is that EN50522 mentioned the relevant points in the system for the touch voltages. And the new version of EN50522 is here now a bit more precise and mentions also that you have to measure outside of the station. In the past, often it was measured only inside the station, but of course, from an operator's point of view, that's understandable. But of course, if you think about pedestrians next to the station touching maybe the fence, that's also relevant. And that's the reason why it's now explicitly mentioned in the standard. Also, potential transfers can occur, which are now explicitly mentioned in the standard. For example, if you have a small local substation and you have connected metallic constructions or other systems like households connected over the PEN connector on the low voltage side, then if you have a fault in your substation, you could also have a ground potential rise at disconnected other systems. And now the standard says you have to consider this. So if you have to measure this and check if all the values are within the permissive limits.
Okay. Oftentimes it will be said that a standard is really a recommendation, but you say you have to. So when you're following or reading the recommendations of the standard, you take it pretty much to heart that that is something you should be doing.
Yeah. So it depends a little bit on the country where you are. For example, here in Austria, we have a local standard which is virtually identical with the 50522. And this local standard is a law, so you must fulfill it. In Germany, the situation is a bit different. There, it's not at the level of a law, but nevertheless, there is a law which says that not this standard specifically, but such standards needs to be applied to be on the safe side. So in many countries, there are some legislative regulations which put some pressure on you to use these standards. And that's for a good reason, because, of course, you can make safer systems using the standards.
Good point.
Okay, so maybe also worth to mention here is if you want to measure these touch voltages, it can be some effort, but here at OMICRON, we have a device which is called our handheld grounding system tester, HTD1, has integrated resistors to simulate the body resistance, which is foreseen in the standards. And it makes it very easy to test these touch voltages. You just connect a plate to it, which simulates your feet, and you touch with a voltage probe. You touch the fans or the doors or the other metallic constructions, can measure the values. And that's a question of seconds, so less than 1 minute. And so you can measure the relevant touch voltages on many different points like fences, doors, and so on, with a very small effort.
Very good. So in regards to EN50522, what are the changes to the standard in relation to these measurements?
Yeah, the changes in the standard, in the new standard of the EN505, different things. For example, in respect to the measurements, it includes now rated distances. So in the past, it contains a certain distance you need to keep for the measurement of the earth impedance or ground impedance. Now these distances were doubled. Also, it includes now a separate chapter for new test methods and interference suppression, and also the introduction of the so-called frequency-selective method. This standard was revised and published in 2022, and in Austria, for example, it was adapted then in 2023.
Okay, and that is where you're based. So how were the measurements carried out before the changes to the standard?
Yeah, typically on smaller grounding systems, one used an auxiliary electrode, which was used to inject the test current in a sufficient distance. And this simulates then a ground fault, and then the voltages were measured to calculate the ground or earth impedance. This is still possible with the new version, and often it's the easiest method. So if you have a transmission tower, it's for sure the easiest method to measure this. However, it requires long test leads. For example, the distances now, as I mentioned before, have also been doubled in the new standard, and the test leads were long before. Now they have to be twice as long, and this is often not possible because even if you have the time, many substations or other transmission towers are in populated areas, and it's often not possible to be in a sufficient distance from the system under test. But the standard mentions also the so-called current voltage method, which usually or typically used a de-energized line for the current injection. So if it was possible to de-energize a line, you could inject the test current via the de-energized line and using the distant grounding system at the other end of the line to inject the test current into the soil. This is a very good method because it provides you results which are very close to reality, because in a real fault, the fault current would also flow in a similar direction. However, if you do this, you need a method to suppress the interferences. For example, if you would test at 50 Hertz or at 60 Hertz, then usually you also have stray currents from energized systems nearby. And if you measure the voltage, you would measure the voltage of these stray currents or caused by these stray currents, and also the voltage caused by the test current. So what you measure is the sum of both. And so it's very hard to separate between the test current or the effects of the test current and the effects of the stray currents. And the old standard and the new standard contain methods to deal with this. For example, the bead method or the polarity reversal method. They have been used in the past. And for this method, you used a large test track or generator in substation, which was not very convenient.
Very good. Okay, so now the test can also be performed with lower test currents, but why is a certain power level still needed if the test current isn't as important?
Yeah, for the grounding measurements or the earthing measurements, the test current is injected in a certain distance. So in large substations, this can be even dozens of kilometers. So we can use as mentioned before, de-energized cables or high voltage line to inject this test current. And this requires significant higher power due to the resistance of this de-energized cable or line. For this, we have test sets like the CPC100 plus the CPCU1, and we can use these test sets to provide the required voltage, depending on the impedance of the line. And for smaller systems, such a high current is not required because the distances are closer, and usually our small battery power test set Compano 100 can be used for that.
Josef, how far should the distance be during the measurements? And what does this mean for conducting measurements?
The standard contains here different sections, for example, for the so-called earth testers. And here the EN50522 mentions 4 times the maximum diameter of the grounding system under test, but at least 40 meters. And that's for the injection of the test current. And this has now changed to 8 times. So it has doubled in practice. That means that for most systems now significantly larger distances are needed. And of course, that can be some effort in practice because you have to walk further away. Maybe you have to cross roads and so on. Before, so the old standard also mentioned 2.5 times the diameter in the measurement direction, but at least 20 meters for the measurement of the voltage. So that was, inject the test current and measure then the voltage in this 2.5 times the distance. This distance has now been doubled to 5 times the diameter in measurement direction. So for the voltage probe, you need to be now much further away than before. And that means that the measurements now take longer due to the greater distances. And the test current injection point is now often out of sight because it's too far away. So it can be also necessary to have additional personnel checking the cable connection to this injection point or be there to ensure that nobody is touching the system during the injection. The positive thing is with the larger distances, usually the results are more reliable. And I guess that's also the reason why they added it to the standard.
Okay, very good. Thank you. So, Josef, you mentioned interference suppression earlier. What methods are available to suppress interference?
That's also a good question because you have all these interferences of the stray currents, which are always in the earth, returning currents in power systems, and they cause a voltage via the resistance of the earth. And you have to separate this voltage from the voltage which is generated by the test current. And there are different methods used in the past. For example, the beat method. In the beat method, you are using a different frequency and use a very high power. And due to the very high power and the different frequency, you can get the superposition of both signals, and then you can mathematically calculate the effects of your test current. The disadvantage is you need a very high power, otherwise it's not possible. The same for the polarity reversal method. For the polarity reversal method, you use the same frequency that's usually generated with a transformer. You inject then the current into the de-energized overhead line or cable, and you do it once with a certain polarity, and then a second measurement with the reverse polarity. And then you can mathematically remove the effect of the stray currents, but only if you assume that the stray current remains constant during both measurements, which is not always the case. The new version of the standard EN50522 has fortunately a new method which is called the frequency-selective method. And actually that's the method OMICRON is using since a long time. And it's also considered now state-of-the-art, and it's explicitly mentioned in the standard. And here we use different measurement frequencies to get rid of the interferences.
Interesting. Could you tell us more about these methods?
Okay, I already mentioned the beat method and the polarity reversal method a bit. For example, for the beat method, I mentioned that you use another frequency. Here, usually you use a big generator, which is on a truck. Then you need a matching transformer. So usually you have a very big truck, which is required to perform these measurements. Also for the polarity reversal, I already explained this a bit. You need very high currents, which requires a big transformer to get this test current. So in the past, it was necessary to do so because this was the only possibility to suppress these interferences. It works quite well, but it's a lot of effort. Nowadays, usually the frequency-selective method is used because that's the much more modern way of testing that. So now we have the frequency-selective method, which is in practical use for about 20 years now, and it's much more modern than the older beat method or the polarity reversal method, which were introduced 30 or 40 years ago. And this frequency selective method was not possible at this time, but nowadays it's technically possible because you need a very accurate source. That's nowadays no problem. And then you need very narrow band filter, which can separate the effects of your test current from the effects of the stray currents or other distortions. So here at OMICRON, we usually use the mains frequency plus minus 20 Hertz. For example, if you have a 50 Hertz main system, then we are using 30 and 70 Hertz. We inject the test current at these frequencies. And then when we measure the voltage, we use very narrow band filter to get only the effect of the test current and not of all the other stray currents. Usually at 30 and 70 Hertz, we have no other distortions, so that works quite well. And it's completely independent if the stray current varies or not. So it's much more reliable than the other methods and requires a much lower current.
Josef, could you go into more detail about the advantages of the newly added frequency-selective method?
Yeah, as I just mentioned, you need much lower currents. So you can work with much lower currents. Of course, if you want, you can also use high currents. But with a rather small test current, you can separate the effects of the test current quite accurately and have good measurement results. And so there's no longer a need for these large transformers or for generators on trucks. And of course, if you have not to deal with all this high voltage equipment, the safety is much higher, because you have less equipment, you have lower power. The other advantage is, of course, the mobility, because if you have a truck, that's, of course, a certain effort. And nowadays, modern test sets like our CPC100, they are below 30 kilograms and can power up to 5 kilo.
Josef, could you summarize the advantages of the newly added frequency-selective method?
Yes, Scott. As mentioned, we can work with lower test currents using this much more modern test method. And therefore, we don't need the large transformers or the generators on the trucks anymore. So no high currents or voltages are needed anymore. This allows us to use small mobile test sets, which are much safer because, of course, they're smaller and they need less current or less voltage. For example, we have the CPC100, which is below 30 kilograms. Nevertheless, it can output up to 5 kilowatt to inject the test current into a de-energized line or cable. And for smaller grounding systems, we have the Compano 100, which is even below 10 kilograms and also very powerful for testing grounding systems. So to summarize it, it's a very good thing that it's now explicitly mentioned in the standard that we can use this frequency selective method. Actually, that's an informal part of the standard, so we could also use it before like we did, but now it's explicitly mentioned and it gives additional safety to our customers that they are doing the right thing.
Very good. Josef, let me ask you another question generally for our listeners who may not be as familiar with earthing or grounding testing. What are you really looking for? And when you have the data, what does it tell you about the substation equipment? What do you need to do as a result of those measurements to improve safety if you find irregular patterns?
Okay, yeah, that's a good question. So actually, the ground impedance or the earth impedance of a substation, it needs to be below a certain limit to ensure safety. Usually, if you have this impedance, it's multiplied with the fault current. This impedance multiplied with the fault current gives you this ground potential rise in case of a fault. And this must be below a certain limit. So if it is too high, then there are different things you can do. For example, of course, you can improve the grounding system, but this is the most expensive solution because it means that you have to dig into the soil, add new metal there, and so on. So a bigger grounding system is usually very expensive. Sometimes that's the only solution, but it's very expensive. There are some other solutions. For example, sometimes it's possible to reduce the fault current. It's only possible in a few cases. The permissive touch voltage is also dependent on the time. So for a short time, a higher touch voltage is allowed. For a long time, a lower touch voltage. For example, because that has to do with the impact on your heart. If you have a high voltage for a short time, it will have no negative effects if it is below a certain limit. If the voltage is there for a much longer time, then it needs to be much lower to have the same safety level. And so what you can do is, and that's what many customers of us do, is to change, for example, the trip times of the protection relays. You have to check your protection scheme if it is possible to adapt the trip times. And sometimes it's possible to reduce it. Then a higher voltage would be allowed. And with this higher voltage, the grounding system would be still considered safe without the change on the grounding system. Because in the case of a fault, you would not be exposed to the voltage for the same long time, but for a shorter time. And therefore, it's then safer.
Very good. Well, thank you for that explanation. So, Josef, thank you very much for joining me in talking about the impact of the new EN50522 standard in this episode of Energy Talks.
Thank you, Scott. It was a pleasure to be here.
Take good care.
Take care, Scott.
And a big thank you to our audience for listening to this and other episodes of Energy Talks. We always welcome your questions and feedback. Please send us an email to podcast@omicronenergy.com. OMICRON has several years of experience in power system testing, data management, and cybersecurity, and offers a matching solution for your application. For more information, visit our website at omicronenergy.com. Please join us for the next episode of Energy Talks. Goodbye for now, everyone.